Hello everybody, and welcome to lecture 3 of the 5 2016 Gifford lectures. As you will possibly recall, we had a gallop through the fundamental physics last week, gallop through the particle zoo, and nothing escaped, unlike London Zoo. And so now we can look forward to stepping back a bit, and the third in the 5 Gifford lectures, Professor Sean Carroll.
Thank you very much. So thanks again for everyone who's here. I don't know if they're taking attendance, but I hope that if you come to all 5 lectures, you get some kind of prize or award or, I don't know, sherry, cup of tea. Yeah, he's in charge of that. But it's true, as Norman just said, we did cover a lot of ground in the last couple of lectures, and the last one in particular. So we learned about the overall evolution of the universe, the little thing called the arrow of time and how that emerges from macroscopic behavior and the growth of entropy. And we learned about the microscopic laws of physics, the core theory that tells us about all the particles and fields that make up you and me. And we tried to make a certain move toward defending the claim that the laws of physics underlying everyday life are completely known. The core theory, which talks about the atoms, the particles, and forces that are inside you, and it describes everything you've ever experienced in your day-to-day goings-on, if you're not using a telescope or a particle accelerator, that is true and will continue to be true as long as we do physics, is the claim that we tried to make. Now today, the lecture seems, at first glance, to be a little bit more abstract and philosophical, but it's really crucial to understanding how the bigger picture, in fact, fits together. So we're going to talk about the concept of emergence. Remember how poetic naturalism makes the claim that there is only one world, the natural world, but there are many ways of talking about that natural world. And if these ways of talking are all accurate, if they tell you something true about the world, then the various concepts and constituents that play a role in these ways of talking deserve to be called real. They really exist. So that sounds benign enough, but obviously it raises a lot of issues remaining to be clarified. How do all of these different levels fit together? How can multiple things be real at the same time, and so forth? And that's going to be the topic of today's lecture. Emergence is the big theme here, and the basic idea is that there are multiple levels of description. We already gave you a cartoon of this back in lecture 1. Here's a different cartoon with a little bit more details filled in. I really want to emphasize that you shouldn't take this cartoon too seriously. The idea of understanding all of the different ways that we can talk about the world and all the relationships between them deserves very, very careful, rigorous study that I'm not going to give it in this lecture. We just want to clear out a little bit of the underbrush. This is a very philosophically simplistic view of things, but I think it captures the eventual truth, the ultimate truths, the big part of the truth. The idea being that in our world, in the world we actually live in, there's this nice way of talking about emergence that relates to scales of distance and time in the universe. On small scales, we need to talk a language of particle physics or atoms or quantum field theory. As we get to larger scales, we can start talking about chemistry and agglomerations of particles, and then we can even start talking about biology and living organisms, and finally psychology and sociology and economics. And all of these higher levels are said to emerge out of the lower levels. So we want to sort of get at what that really means. And in particular, there's one part of this system of things that we really want to emphasize over and over again, which is that not only do you take small things and bundle them up to make big things, but the big things you make can be completely different kinds of things than the little things they're made out of. Okay? I don't know whether that sounds obviously true or impossible to believe to you, but the thing that we really need to establish is that entirely different concepts and ideas can come into being at the emergent levels. Now, even the fact that the lower levels are in some sense lower and made of smaller scales, all of this is contentious and up for grabs and has something to do with how our actual world is constituted, not necessarily part of hypothetical alternative worlds you could imagine. So we're going to be leaning a lot on aspects of the actual world to make this come true. And in fact, the very first thing I want to do is to use this idea of emergence to kind of put a parenthesis on the idea we were talking about in the last lecture. Remember the claim, the laws of physics underlying everyday life are completely understood. What we made the argument for is that given that the world is described by quantum field theory, we can use the rules of quantum field theory to say that we know what the fields are. We know what the particles and forces are that are operating inside you and me. There's still the claim, and I addressed it a tiny bit, but would like to do a little bit better, that quantum field theory is the right way of thinking about the world. We have enormous experimental evidence that quantum field theory is the right way to be thinking about particle physics. That I'm just going to take for granted. But could there be levels underneath quantum field theory? After all, if we don't understand gravity at the deepest level, we don't even know if space and time are really fundamental. My attitude is going to be, maybe they're not fundamental. That is completely okay. I'm making no claims about fundamentalness, but it won't matter. The important thing is that at the level of the atoms and particles that are inside your body, I'm perfectly welcome to use the rigorous framework of quantum field theory. And the reason why I can do this is an idea called effective field theory. And this is once again traced back to Ken Wilson, same guy whose picture I showed last time, a brilliant, underappreciated physicist who did work in the 60s and 70s. Wilson was really, it's fair to say, the first person to understand how quantum field theory works. Field theory goes back to people like Dirac and Fermi, and obviously people like Feynman and Schwinger and Tominaga made enormous contributions to it. In some sense, Wilson was the one who figured it out. And the way that he did it was to say, the thing about fields is, you can think of fields as being decomposed into different wavelengths. There are short wavelength vibrations and there are long wavelength vibrations. Last time we put this idea to work to say, is a particular field or particle accessible to us? If it only is a very, very short wavelength vibration, then maybe we can't see it. But Wilson went beyond that. He said, take some field theory that you're working with. You know, quantum electrodynamics, for example, is the field theory of just electrons and photons. You could take the standard model of particle physics or any number of other interesting and well-studied quantum field theories. And Wilson says, take your fields, stretching throughout all the universe, write them as a sum of high-frequency vibrations with short wavelengths plus medium-frequency vibrations with medium wavelengths plus low-frequency vibrations with long wavelengths. And you notice that in quantum field theory, there's a relationship between energy, which is equal to mass, because E equals mc squared, and is closely related to momentum under relativity. So energy, mass, momentum are inversely proportional to wavelength. Things that have short wavelengths are very energetic. This seems a little bit counterintuitive sometimes. You think that a small thing is less energetic, but it needs to really fit into a very tiny region, and that fitting that in there, think of it squeezing a spring together. You're putting energy into it. That's basically how quantum field theory works. So Wilson says, I can divide all of the vibrations in my quantum fields into ultraviolet and infrared. He says, you give me some energy scale, I don't care what it is, and I'm going to divide all the vibrations in my fields to those at higher energies and those at lower energies. Ultraviolet is just borrowed from the visible light idea, right? Ultraviolet is short wavelengths. Infrared is long wavelengths. So ultraviolet is high energy, infrared is low energy. And what Wilson noticed is that many of the difficulties with quantum field theory, you know, there were all these puzzles in the 1940s and 50s and 60s about infinities. And you might have heard that infinities get swept under the rug and renormalized, and it's all very confusing. What Wilson realized is that all this confusion, all these infinities, came from taking arbitrarily high energy excitations with the utmost seriousness, really believing that these very, very short wavelengths were there and contributing to your processes in quantum field theory. And Wilson says, you don't know that. You don't see these things. They're too high energy. You can't make them. You can't detect them. They play a role in your calculation, but maybe they don't. Maybe you don't need them. Maybe there's something completely different going on at very high energies that you don't know about. So what he suggested is, don't worry. It was a brilliant idea. Not worrying is always a brilliant strategy. So Wilson says, let's just not worry about anything that is ultraviolet, anything that is at high energies, all the short wavelength vibrations in our quantum fields. The reason, of course, why that's better than just an encouraging motto for going through life is that what Wilson showed is that if you only look at the low energy, long wavelength part of your quantum field theory, you can still do quantum field theory. You can do all those Feynman diagrams and scattering experiments. You can measure parameters. You can describe the phenomena in the infrared in terms only of other phenomena in the infrared. You never need to know what's happening in the ultraviolet. So for example, remember I showed you these Feynman diagrams. Feynman diagrams are a way of saying how likely a process is to happen. So in the top level here, we have the idea of one particle decaying into two. And what Feynman and all of the people who worked on field theory in the 40s and 50s were able to show was that if you want to calculate this process, one particle decaying into two, it's not just one diagram. The end result is this sum of many, many diagrams. In fact, how many diagrams? Infinitely many. And this is what the problem is, right? And that's because, as you see on the right, there's many different ways you can connect together these tinker toys, these little vertices and edges, to make a graph that could represent different particles popping in and out of existence in the Feynman diagram. Likewise, on the next level, you see two particles coming in and interacting, and they go their own ways. And again, there's an infinite number of diagrams that contribute to this. So Wilson says the following thing. Imagine you have a real, complete, happy quantum field theory that is good all the way up to the ultraviolet. All the energies are there. Now just ignore the ultraviolet parts. Remove from your calculations all the short wavelength parts of those quantum fields, except insofar as they would affect what happens to the infrared particles. In other words, imagine that all of your outside lines, not the internal ones, but the external ones, imagine that all the external ones are low mass, accessible particles. Inside, all sorts of things could be happening. What Wilson is saying is, ignore the right-hand side of this equation. All I care about is the blob on the left-hand side. One particle, blob, decaying into two. Two particles, blob, splitting back into two. That's what I really care about. So he says, I can write down the theory of the blobs. I don't need to know all the details of all the intricate Feynman diagrams in between. And the miracle is that what pops out from just those blobs in which I have ignored, renormalized away the ultraviolet effects is still a quantum field theory that is perfectly sensible in its own right. In other words, I can still do quantum field theory at low energies, the quantum field theory of the particles I get to know about in my everyday life, without knowing everything about everything all the way up to arbitrarily high energies. That's the idea of what is called an effective field theory. It's a theory that is only supposed to tell you what happens at energies below a certain threshold, presumably energies that you can access. We've done experiments up to energies roughly 1,000 times the mass of a proton. That's basically where we know our effective field theories are good when we talk about the core theory of particle physics. And it's an interesting phenomenon that it's not just that we can ignore things up there near the Planck energy where quantum gravity becomes important. As you lower the cutoff scale, as you lower your distinction between high energy and low energy, as you exclude more and more high energy stuff, the world, as it turns out, is described by a sequence of very different looking effective field theories. For example, the most obvious example in the world is you know that protons and neutrons are made of quarks and gluons. Quarks, the particles inside, gluons are the force carriers of the strong nuclear force that hold those quarks together. The effective field theorist says what you really mean by that is that there's an energy, which we call the QCD scale. QCD is quantum chromodynamics, the theory of those quarks and gluons. Above that energy, if you want to give an accurate picture of protons and neutrons, you must speak the language of quarks and gluons. Below that energy, you don't. Below that energy, you speak the language of neutrons and protons and what are called mesons, pions and eta mesons, and a million different mesons that are basically made out of these quarks and gluons. Not only do you have different ways of describing the high energy stuff and the low energy stuff, you use completely different vocabulary words. You're beginning to see the hint of how emergent theories can use different vocabularies than the more comprehensive theories below them. So in 1933, Enrico Fermi hypothesized an interaction that could explain why neutrons decay. They had recently discovered the neutron, they knew what a neutron was, and they knew that all by itself, put a neutron out there in space, it will decay in a few minutes. It can remain stable inside a certain nucleus, but by itself, the neutron is unstable. It turns into a proton by spitting out an electron in what we now call an antineutrino. So Fermi wrote down a theory, the Fermi theory. Enrico Fermi, a famous Italian-American physicist, he was really the last physicist alive who was one of the world's best theoretical physicists and one of the world's best experimental physicists at the same time. So he wrote down one of the earliest field theories for fermions, because they're named after Fermi. No one has more stuff named after him than Fermi does. And this works perfectly well. Today we know that it's not the whole story. Today we know that that neutron is made of up quarks and down quarks, just like the proton is. And it's not just that a miracle occurs and the neutron decays. What happens in the core theory is that one of those down quarks emits what is called a W boson. This is something that we came to understand in the 60s and 70s with what is called the electroweak theory. And again, if I had a 20-lecture series, you would hear all about the W boson. But today, just believe me, there's something called the W boson. When the down quark emits a W boson, it converts to an up quark, and then that W itself decays into an electron and an antineutrino. The point is, Fermi wasn't wrong. Fermi's way of describing the decay of the neutron works perfectly well as long as you're at a certain energy below what is, guess what, called the Fermi scale, okay? Above it, you need to have this story of W bosons, etc. So this is the kind of match that we have when you believe in emergent levels of reality. There's one way of talking about reality, which is a story of quarks, gluons, W bosons, electrons, antineutrinos. There's another way of talking about reality, which is a story of protons, neutrons, electrons, and antineutrinos. It depends on what question you want to ask. This idea that there are new concepts at different levels is why we don't sweat too much the fact that we don't understand quantum gravity and the nature of space-time itself. This is the reason why we're not worried that future discoveries in fundamental physics will undo the core theory in some way. They might give us a more comprehensive description. They might give us a better description, and that would be great. We're hoping for that. But at its level of applicability, at the energy scales where we think the core theory works, it will continue to work. That's because gravity is very, very weak. There's an energy scale that tells us where quantum gravity becomes important. It's called the Planck scale, after Max Planck. He was the one back in very early in the 20th century. He invented Planck's constant, which is basically characterizing how important quantum mechanics is. And he noticed, it's a hilarious story that doesn't get told enough. So Planck noticed that I have this new constant of nature, my constant. There's other constants of nature lying around. There's Newton's constant for gravity, and there's the speed of light. These seem to be fundamental ingredients of the world. But I can combine them to make sort of absolutely agreed upon scales for space, time, energy, mass. I can make the Planck mass, the Planck time, etc. And the very first thing he thought was, this would be a great way to talk to extraterrestrials. Because they don't know what a meter is, right? But they will know what the Planck time is if they've discovered modern physics. The thing about the Planck energy is that it's huge. It is 1 quadrillion times bigger than the energies that we're exploring at the Large Hadron Collider in Geneva, which are awfully big in their own right. So underneath space and time themselves, many things could be happening. Superstring theory, loop quantum gravity, my favorite thing, which I call quantum emergent gravity, because I like the word emergence. And we don't know. These are all very fundamentally different ultraviolet theories of what would happen at very high energies. The point of effective field theory is it doesn't matter. At low energies, long wavelengths, things that are below the Planck scale, which everything in this room is, everything you've ever experienced is, everything you've ever seen in nature is well below the Planck scale. Space and time obey the rules of general relativity, and quantum field theory and the core theory work perfectly fine. Now, we've opened up a can of worms here, though, of course. What we're admitting is that we don't have any right to believe quantum field theory beyond the Planck scale. Really, the world at its most fundamental could be utterly different than quantum field theory. My message is that that's okay. Just to emphasize how different it could be, I will give you a couple of buzzwords you can use at cocktail parties to impress your friends, or even get down to the pub. Something called the gauge gravity correspondence, or the ADS-CFT correspondence. This is an idea that came about in the mid-1990s due to a brilliant Argentinian-American physicist, Juan Maldacena. And what he was invoking was the idea of a duality. A duality is when you have a single theory, a single way that stuff can happen at some fundamental level, but which can look very different depending on what question you ask about it. What Maldacena showed is that there's a duality between a certain kind of quantum field theory without gravity, in particular what is called a conformal field theory, and in very particular, if you really want to impress your friends, n equals 4 super Yang-Mills theory at strong coupling, okay? Go ahead, write that down. He says that this is a theory without gravity that let's imagine exists in a 4-dimensional space-time, okay? There's no gravity there, it's just quantum field theory. We can ask the questions and we can answer them. He says there's another theory, which is quantum gravity, in particular string theory, with a negative vacuum energy, which is a space-time called anti-de Sitter space. This 5-dimensional anti-de Sitter space looks like a cylinder, and you can take this 4-dimensional flat space-time and wrap it around the boundary, and imagine 2 seemingly completely different theories. Gravity in this 5-dimensional space-time with a negative vacuum energy, no gravity in this 4-dimensional space-time on the boundary. Maldacena argued that these are really the same theory. This is an example of what is called the holographic principle, which is more or less a conjecture that we have lots of evidence for right now, but we don't know that it's true. But the idea seems to be that whenever there is gravity, the number of degrees of freedom, the amount of information you need to describe what's happening in the world, takes up 1 less spatial dimension than you thought. If you live in a world of quantum gravity, Maldacena is saying in particular, with 4 dimensions of space and 1 of time, really it's equivalent to only 3 dimensions of space in a world without gravity. The only reason I'm telling you this is to boggle your mind, to make you realize that the kinds of descriptions we can have at the very deepest levels just look very, very different. We have 3 dimensions of space in this room right now. We also have gravity. The holographic principle would suggest maybe there is a 2-dimensional world without gravity that is equivalent to the 3-dimensional world that we live in, that we emerge out of this 2-dimensional world via some kind of hologram. We don't know if it's true. That's the kind of thing that is on the table. So this reasoning is why I was able to draw this arrow and cross it out. This was the diagram representing the relationship between the core theory that we think we know and these other parts of the world that we don't think we know. We don't have very good theories of higher level phenomena such as biology or astrophysical phenomena like dark matter. We also don't have anything underlying the core theory. This is why I don't care. I mean, I do care because I'm a theoretical physicist and I want to get that, but for the statement that the core theory works, I don't need to know what lies beneath it, because the core, no matter what lies beneath it, in the infrared low energy world, it will look like an effective quantum field theory, the core theory. Now, you might want to ask, here's a question that I'm not going to give you a satisfactory answer to. Why does any of this work? We could imagine a world where there was no such thing as emergence. We could imagine a world in which there was a correct way of talking about it and no other ways. You couldn't throw away some of the stuff. All that ever happens, what happens over and over again, we talk about an emergent level of reality, is that you are intentionally forgetting some things about the world. When we talk about the core theory, we're intentionally not paying attention to what happens in quantum gravity. When you talk about the air in this room as a fluid, a gas with a temperature and a pressure, We are intentionally not thinking about the individual molecules of which it is made. And yet, you get a really good way of talking about the air in this room. Why does this work? I think it's fair to say we really don't know. This is something to work on for you young graduate students out there. It might not get you a job, sorry about that, but it is a fundamentally important question to understand not just how emergence happens in the world, but what are the general conditions under which it might happen, and why is our world like that? We think it must have something to do with the idea of locality. That is to say, we live in a world where if you have two particles, they will interact with each other when they're close to each other, when they are located nearby in space and in time. If you think about classical mechanics, right? You have a particle, a baseball, I guess football, cricket ball, I don't know what you guys have over here. Some ball that's going to be moving through the world. Isaac Newton says, give me its position, give me its momentum, I will tell you what happens next. When the position of two balls is the same, they will interact with each other. Not when the momentum of two balls is the same. There's no locality in momentum space. There's something called space in which interactions are local, and somehow that crucial feature of the world seems to enable the emergence of higher level descriptions. But I would love to know more about why that actually happened. So I'm going to be repeating myself a lot here, but because I really want to emphasize this, because this is one of those things where when I say it the first time, you will nod and say, yes, of course that's true, get on with it. By the end of the lecture, you're going to say, no, 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 that's completely false, even though I'm saying the same thing that I started saying, because we'll apply it in different regimes. What is the relationship between the emergent levels and the underlying comprehensive microscopic levels? The claim I want to make is that there really is new knowledge contained in knowing the emergent theory, even if the emergent theory in principle is completely compatible with the underlying theory. So from my perspective, what I will be talking about, the emergent behavior must always be consistent with the underlying description. If you have a way of talking about the air in this room as a fluid with a temperature and pressure, it better not violate the laws of what is called kinetic theory, the atoms and molecules bumping together. They have to be consistent. In some sense, the emergent behavior is entailed by the underlying description. You don't need to know the emergent behavior. If you wanted to, if you were Laplace's demon, someone could give you the position and velocity of every single molecule of air in this room, and Laplace's demon could crank through the calculations and tell you what would happen next. You don't need to know those emergent levels. In fact, typically the emergent levels are not derivable. So I'm very intentionally invoking Laplace's demon, who has infinite calculational power. Very often an objection to emergence is said that, or an objection to this idea that the higher level theories should be entailed by the lower level ones is, but maybe you can't derive the higher level theory from the lower level one. For the case of the air in this room, we can derive it. For the effective field theory example from Ken Wilson, we can derive it. But can you derive biology from the core theory of particle physics? My claim is, no, of course I can't. Don't be silly. But nevertheless, it better be consistent. Okay? I don't think this is an objection at all to this kind of interlocking way of thinking about the different levels of reality. However, we are not Laplace's demon. Hypothetical thought experiments involving infinitely smart demons only get us so far. Because we don't have infinite calculational power, that's why it is truly new knowledge when we discover, whether it's through derivation or through empirical investigation, emergent ways of talking about the world. Because the fact that the air in this room can be described by a fluid obeying the Navier-Stokes equations, the fluid mechanics equations, that's a highly non-trivial piece of information that you wouldn't obviously guess if someone just handed you a list of atoms and molecules. Knowing that there is a different way of looking at it is in fact a piece of knowledge that is not automatically transparent when you only have the more comprehensive theory. And there are new realities, which is going to be a slightly more controversial thing that I want to say. So it's going to, again, start out as uncontroversial. I think that this table is real. There you go. I think if you give me that, if you agree with me that the table is real, you're going to agree with everything I say for the rest of the lecture, okay? But you're going to, the worry is that you're going to start agreeing with me that the table is real and then go back later. So the table, the idea of a table, is not there in the core theory, right? There's no part of that equation that I showed you that says here are tables, right? There's electrons, there's quarks, there's photons, etc. The idea of a table is a macroscopic emergent phenomena, just like the idea of the temperature in this room is a macroscopic emergent phenomena. My claim is that if you have an emergent level of reality that works, a description, a vocabulary, a story to tell about the world, that refers to the world at some level of remove, so you are not giving me all of the information but just some of it, and that emergent vocabulary works, it's scientifically testable, it makes good predictions and so forth, then the elements of that theory deserve to be called real, whether it's tables or the temperature of the air in this room. And of course, eventually what will matter is human consciousness. This is where it's going to get difficult. And free will, of course. We're going to get even more difficult when we get to right and wrong, okay? There's different ways of talking about the world. I do not think that consciousness is an illusion. I think that it's an emergent phenomenon that is entailed by the particles and fields that you're made up of. It's not an illusion. It's there. It's just as there as this table is. It is a new reality that is not obviously present if I just give you the equation for the core theory. Okay, so this is just to reiterate. It's obviously true that you understand something better about the world if you know not only the comprehensive description, but also an emergent one. In principle, if I'm Laplace's demon, I can solve all the equations for all the molecules of air in this room, but it's a lot of equations. 10 to the 30 is the number you should have in mind for a big macroscopic collection of atoms and molecules. It's hard to solve those equations. The number of equations you have to solve, if you think about the air as a fluid with the temperature and pressure, is of order 1 equation. It's much easier to solve that. So as a matter of simple efficiency, if you want to know what happens in the world when you have incomplete information and sub-infinite calculational power, effective theories, emergent theories, give you that ability and therefore give you new knowledge. That's one of the reasons why we should count them as real. And again, you're totally willing to believe me when I'm talking about air in the room. Let's see how far you're willing to follow me. It's not only new nouns that we have when we go from a lower comprehensive level to a higher emergent level. There's new ways of talking that come in, new principles, new concepts. So remember we talked about the arrow of time, right? And I made the claim that all the differences in our world between the past and the future can be traced to the fact that entropy used to be low in the past. And that is something we can call econological. You might have heard of the word teleological. Teleological means directed towards some future goal. Econological means based on some past starting point. It's a word that I made up on my blog. I didn't know it because it's a Greek word. I don't speak Greek, but I wrote a little blog post saying what word should we use for this concept, and one of my commenters helpfully chimed in. Econological, driven from the past rather than directed toward some future goal, okay? This is how, as far as we know at our best comprehensive level of reality, the real world works. It is not teleological, it is econological. So, you might want to know, is the entire concept of teleology just a waste of time because it is nowhere to be found in this deep level of talking about reality? And I want to say, no, that is going too far. The question that you should ask yourself at every level of reality is what are the applicable concepts? It is entirely possible that there is an emergent theory of some aspect of reality that is best described as teleological. Teleology can be thought of as saying that no matter what you know about the world now, there is some future goal towards which it is directed. That's not the way the universe as a whole works, but it could very well be the way some little part of the universe is working. And if we have an emergent description for which that is true, my claim is that we should treat that as the real description of that part of the world. Let me give you an example of teleology in action. Here's a cat with its eyes on a mouse, okay? I might want to ask the question, what is the cat doing? What is the best way we have of describing the cat? If you're slightly too hardcore of a reductionist, you might want to say, well, I'm just going to list for you all the molecules in the cat, all the atoms in the mouse, and I'm going to be Laplace's demon and solve the equations of the core theory. I, on the other hand, am happy to work at the emergent level, and I'm going to say that cat would like to catch the mouse. It is trying to catch the mouse. It has a goal, if you like. It has a telos. It has a purpose. And that's a completely okay thing to believe in. You don't need to think that the idea, the claim, the cat has the purpose of catching the mouse is an illusion. It is not illusory. It is completely an efficient, real description of the world at a certain level of precision, in a certain emergent version of the laws of physics, of reality, regardless of the fact that the very concept of a purpose, the very concept of a telos, is not to be found in the underlying laws, okay? So the things that appear to us in the emergent theories are more than just groupings of the things that appear to us in the microscopic theories. Wholly new ideas might come into play. Now I have a footnote. Occasionally in the series of lectures I need to footnote because some people know too much. Some people have been reading the wrong books, and I need to explain what I don't mean as well as what I do mean. There is in the literature a distinction between what might be called weak emergence and strong emergence. Everything that I have been saying and will say falls under the category of weak emergence. Weak emergence says that there can very well be new concepts, new behaviors at the higher emergent level of reality, but in principle, Laplace's demon still works. In principle, I could just describe the system at the lower level, put it on a computer, simulate it, and get the right answer. So no matter what the air in the room, this room is doing, in principle, there is a list of what all the atoms are doing that I could put on a computer and find out what's going to happen at the end of the day. The idea of strong emergence is separate and I think wrong. So this is my claim, you can believe it or not. Strong emergence says that higher levels not only have new concepts associated with them, but exhibit behaviors that even in principle cannot be reduced to what happens at the lower levels. That even in principle you could not imagine describing things wholly at the lower, more comprehensive level, evolving forward in time and getting the right answer. There is something truly new, truly otherwise uncapturable at the higher level. So there's a very, very fine distinction here. I'm admitting, I'm in fact strongly advocating that new ideas, new realities, new knowledge exists when you have an emergent higher level description. But I'm also insisting that in principle, I don't need it. I could still take the fundamental description and put it on a computer. A strong emergentist says there's something truly different about the higher level, something that cannot be captured at the lower levels. As far as I can tell, almost everyone who believes in strong emergence does so because they don't think that human behavior can be captured by the laws of physics. They think that we are more than collections of atoms, particles, obeying the equation of the core theory that I showed you. Human volition, will, a sense of right and wrong can't be reduced to these lower level things. I don't think that there is any actual experimental data that you can cleanly point to and say, aha, there, strong emergence. So this is an ongoing debate in the community. I'm going to go with weak emergence for the rest of what I'm talking about. Now, I think that there is one principle of emergence that helps clear up almost all of the problems that people can run into. And in honor of the new Ghostbusters reboot, I've dubbed it, Do Not Cross the Streams. Those of you who saw the original Ghostbusters movie, those of you from my generation, is an important thing when you have your plasma weapon and you're shooting at the ghosts. Don't let the streams cross, everything will blow up. Of course, at the end of the movie, you have to do that, so it's not very good advice. But the idea here is that when you have a comprehensive description of reality, or let's just say some more fine-grained description of reality, and on top of that you have some emergent description of reality, the simple way of thinking about it is never start a sentence in one level and then end it in another level. It sounds like a simple maxim. My promise to you is that if you avoid making that one mistake, your life will be much, much easier when dealing with emergent levels of reality. There's a whole bunch of mistakes and confusions that can arise from mixing up the levels, from insisting that I can talk at the same time using one description and another one. That I talk about the air in this room as having a temperature and a density and 10 to the 30 molecules with positions and velocities. My position is it's or, not and. So let me give you examples of why crossing the streams is a bad idea. There is an idea called downward causation. I don't like either one of these words, downward or causation, in this particular context. But the idea is that is a strong emergent idea. It says that microscopic theories by themselves don't give you the whole story. You can't explain what happens even at the micro level in terms only of the micro theory. You need to have some information about what happens at the higher levels. Sometimes this is put more technically as saying higher levels act causally on lower levels. So two examples. This is one of those things I have to apologize. I totally don't believe in downward causation. So I actually have difficulty explaining it. You know, it's one of those things where you so think it's wrong that you struggle to give it its best, the case for it, which you should be able to do. So, but I'm going to try. Two examples. One that I get from other people. I don't make them up myself. So one is snowflake formation, right? I mean, it's a wonderful set of physics and chemistry involved in understanding how snowflakes form, why they have the hexagonal symmetry, why they're all different in various ways, and you get to take pretty pictures while doing it. So the downward causation claim would be that you can't truly understand what a certain water molecule that is being accreted onto the snowflake is really doing unless you know that it's part of a snowflake, okay? You can't even in principle just give me the list of all the water molecules, all the equations for molecular motions, and expect to get a snowflake out at the end. You need that higher level description. Another example given by John Searle. John Searle, of course, one of the leading philosophers of the late 20th century. I keep picking on him because I disagree with him about various things. And if you're going to disagree with somebody, disagree with the best, right? Don't pick the straw men. So Searle gets an enormous amount of credit, but I think that he's missing something important here. He gives the example of hammering a nail, okay? Something very down to earth. There's no secret hidden physics there. But he says, look, the hammer's made of atoms. The nail is made of atoms. When I hit the nail with the hammer, it is clear that the fact that the hammer is a solid object is causally efficacious. When I talk about the hammer hitting the nail, the fact that the hammer is solid helps me understand why the nail goes down. And he says that is not knowledge that you would have even though both the hammer and the nail are completely made of atoms. So what I want to say to both of these is, you know, of course, in principle, I could understand snowflakes being made just at the level of atoms and molecules. If you don't believe that, if you truly don't believe that I can understand either how hammers hit nails or how snowflakes form just through atomic physics and the elements of the core theory, well, that core theory equation that I gave you makes a prediction for what these molecules are going to do, whether they're in a hammer or in a snowflake. So if you don't think that I can explain that, then you must think the core theory is wrong. You must think that equation must not give you the right answer because it gives you an answer. This is what is called the causal closure argument in the philosophical literature. You tell me what the molecules of water are doing, I could plug into the core theory what's going to happen next. It will tell me an answer. Either it says there's going to be a snowflake or there's not. So for the example of the hammer hitting the nail, is the solidity of the hammer causally efficacious? Sure, if you are speaking the language of hammers and nails. The only mistake is that when you start speaking one language and switch to another one. I have a hammer that is solid and it hits the nail which is made of atoms. Clearly the solidity of the hammer was acting on the atoms, right? No, I think that that is a wrong way of thinking it. Either tell me what's happening at the level of hammers and nails or at the level of atoms. Don't claim to be overthrowing the most fundamental laws of physics because you started a sentence in one language and ended up in the other. And once again, of course, the real reason why people want to talk this way is because they don't want us to someday explain, or they don't, well, be a little more fair. They don't believe that we will be able to someday explain human consciousness in a way that is utterly, in principle, explained by the laws of the core theory. So, again, this is just a claim that I'm making, and I think we have experimental evidence to back it up. In the world as we know it, there is no downward causation. The way that emergence actually works is more or less according to this picture. On the left, you have the fine-grained view of the world, all these tiny little squares. On the right, you have some emergent view of the world, the bigger squares. And there is a map between them, the emergence map, as I put it. So if you look at the red box on the left, this is a region of all the possible states of your microscopic theory, what you call a macrostate, a collection of some of the different ways the different pieces of the microscopic theory could be arranged. And the emergence map takes several different possible microscopic arrangements to one particular macroscopic arrangement. Remember how Boltzmann talked about entropy? He said, you don't know the position and velocity of all the air molecules in this room, you just know some coarse features of them. That's what emergence does. He says there's many different possible arrangements of the air molecules in this room that have exactly the same temperature and density and pressure. And the emergence map takes all those many possible microstates and maps it to a single macrostate. And then the idea, if you have a successful theory of emergence, you could either take the specific microscopic state you start in, evolve it forward in time, and then map it via the emergence map to some macroscopic state, or take the initial microscopic state you started in, map it via the emergence map to some macroscopic state, and then evolve it forward in time using the macroscopic rules. And you better end up in the same place at least almost all of the time. And in the examples we understand, whether it's thermodynamics or effective field theories, that's precisely what happens. So the problem with downward causation is not that lower levels can causally influence higher levels, but not vice versa. The problem is that levels don't causally influence each other at all. It's not a causal relationship between different levels. When you talk about causes and effects, stick to a single level at a time. Emergence and entailment and consistency relate the different levels, but causality works within levels one at a time. A second example where I think that people go wrong by crossing streams is the extremely contentious issue of free will. Do we have free will? You might, given how strongly I've been pro-physics and pro-science so far, be surprised to learn that I want to say, yes, we do have free will in a certain sense. It depends on how you define free will, of course, and that becomes the most boring argument in the philosophy of science, if you're arguing over what is the best definition for something. If what you mean by free will is, can I think my way into violating the laws of physics, then no, I don't believe that. If what you mean by free will is, can I as a human person decide what to do next, then yes, I do believe that. And I think that this is a different issue that we have in front of us. In the sense that I can think of you as a collection of atoms and particles obeying the laws of physics, if that's the information you give me about yourself, and I'm Laplace's demon, at that level there is no free will. I can just solve the equation and I know what you will do next. How many times in human history has someone been given all of the microscopic information about all of the atoms and molecules in their body and then solved the core theory equation forward in time? 0 times. That never happens, and that never will happen. We never know that much about our actual state. Therefore, that's not how we talk about ourselves. We talk about ourselves at an emergent, higher-level description where we're people. People with ideas about what we want, desires and cares and values, and people who make decisions. Even the most strident free will skeptic in their actual everyday lives talks about themselves as making decisions. My claim is that that's all you need to say that free will exists. If the best theory you have of people, the best emergent way you have of talking about human beings at the level of their macroscopic personhood is one that involves vocabulary words like I made a decision or this person chose to do something, then clearly in that level of description there is something called volition, the act of making a choice, and that's what we mean when we say free will exists as an emergent phenomenon. So 2 footnotes to that. It might be that we can imagine circumstances under which our free will disappears. This existence of free will is not a hard and fast thing. It relies on the fact that our best theory of human beings has them making choices. They're unpredictable in some sense. There are people who become predictable. This becomes not a philosophy discussion, but an extremely important legal and political and social discussion when you talk about how to punish people, how to assign responsibility and blame to actors in the world. If you read in my book, I tell the story of a man who had a brain tumor, and it seems the claim was, it's always hard because there was a legal case, the claim was while he had this brain tumor, he was driven to child pornography. He watched it on the internet and so forth. They removed the brain tumor, his desire for child pornography went away. But it then came back, he got the brain tumor again, and again back with the child pornography. And his legal defense was he couldn't help it. He was determined by the fact that his brain was failing to have these desires. The case itself is extremely sketchy. I wouldn't draw too many conclusions from it. But in principle, we can imagine having a theory of some human beings that makes them absolutely predictable. With available macroscopic information, we know exactly what they're going to do next. When and if that becomes the case, I'm happy to say that those people don't have free will. But in the meantime, most people who I know really do. The other issue is sometimes free will is defined as the ability to have acted otherwise. And you say, you know, if you obey the laws of physics, you had no ability to act otherwise. But there always needs to be another clause here, the ability to act otherwise given certain information. And again, given the macroscopic information to which we have access, you do have the ability to act according to the macroscopic laws of physics. So in that sense, I think it's perfectly okay to talk about free will. If you don't like that sense, that's perfectly okay. You can be my guest. So just to put a little punctuation mark on this, sometimes when people worry about determinism, they mix it up with predestination. They're slightly different concepts. Putting aside quantum mechanics, let's imagine a limit in which the laws of the atoms and molecules of which we are made are really deterministic. We know exactly what's going to happen. So in principle, Laplace's demon knows exactly the future of the universe. Sometimes we worry that that's like being told our fortune, being told where we will end up. You will grow up to be a beautiful princess and marry a handsome prince, okay? That's never what predestination is, never what determinism is actually like, because it's not predestination. Because the idea of predestination involves a very specific, simple future state that you will end up in. The idea of actual Laplacian determinism says that if you knew everything about the world right now, you could in principle say what's going to happen in the future, but we never have that information. So in fact, determinism is not like some spooky 3 sisters telling you what's going to happen to your future ambitions for the Scottish crown, for example. Rather, it is like an annoying little kid. This is what the universe is like in a Laplacian deterministic cosmos. The universe is like an annoying kid who comes up to you and says, I know what's going to happen to you next, and I know what you're going to do. So you say to the kid, all right, tell me, what's going to happen to me? What am I going to do? And the universe says, I can't tell you that. And then something happens, and the universe says, you see, I knew that was what's going to happen. That's how determinism actually works in the world. It is completely inaccessible to us in practice. So the fact of microscopic determinism doesn't stop us from believing in a macroscopic theory with ability to make choices. Okay, the final topic then is 2 subtopics here. One of the things that emerges when you go from the micro to the macro is the very idea of a reason why something is true. We can imagine that at the microscopic level of reality, Laplace would teach us all we have is a state of the universe and an equation that tells us where it's going to go. As I emphasized in the first lecture, there's no idea of a cause or a reason why or an explanation embedded in the core theory of nature. These are labels that we attach to it ex post facto because they are emergent phenomena. So here again is Professor Leibniz, who promulgated the principle of sufficient reason. Nothing is without a ground or reason why it is. Whereas a poetic naturalist says, well, sometimes there's a ground or reason why things are the way they are, but maybe sometimes they're not. The real question is, are they obeying the laws of nature? That's more or less the most we can ever ask. Just like cause and effect, just like our ability to associate a particular cause with a future effect can ultimately be traced to entropy in the arrow of time, the fact that certain features of the world have what we call explanations for them might only exist at this higher emergent level of reality. So for example, talk about a giraffe. Once again, just like the cat chasing the mouse, you could describe a giraffe. You could say, why is the giraffe like that with the long neck? So Laplace, if he were here, would say, oh, that's easy. Just tell me exactly the quantum state of the early universe and give me all the laws of physics, and I will evolve it forward in time, and there will the giraffe be at the end of the day, at least on some branch of the wave function of the universe. That's a true statement and is completely useless in answering the actual question, why is the giraffe's neck like that? Another explanation, another answer is, well, there's food up there, high up. Way back in evolutionary history, there was a mutation that made the necks of some giraffes a little bit longer. They could get to food that their competitors could not get to. That mutation was selected for by natural selection, and now the neck is very, very long. That is just as true. Of course, biologists argue over whether or not that is true. There's other theories for why giraffe necks are long, but there is a theory, is the point. There is some correct explanation. That explanation is part of this emergent higher level way of talking about the giraffe. In that level, it is perfectly okay to say the purpose, the reason why there is a long neck on a giraffe is because it needs to be able to get the food high up there on the trees, even though purposes and reasons why would not have been part of a purely Laplacian microscopic explanation. The most deep and profound level at which we can address this question is the universe itself. Here's something that philosopher Adolf Grünbaum calls the primordial existential question. Why does the universe exist at all? Why is there something rather than nothing? This is the one, literally, you know, I got interested in physics and cosmology when I was 10 years old, reading books in the library, black holes, quarks, all this was awesome. It got me thinking about the universe. And by the time I was 11 or 12, I would sometimes, while falling asleep in bed, start thinking like, well, what if there even hadn't been a universe? And that was it. There was no more sleep for me that night once I started thinking about the absence of a universe entirely. So it's a very natural thing to ask, why is there a universe? What is the deep explanation for our very existence here? So here's the universe as we've already plotted it out. Well, one of the things in the modern world, if you want to find an answer to a difficult question, you might consult the internet. You don't want to look at Wikipedia because anyone can put anything on Wikipedia. But there is, for deep questions like this, something called the Stanford Encyclopedia of Philosophy, an online, free, peer-reviewed, professionally written resource that gives you, it's a wonderful thing. You can read about all the big topics in philosophy. And there's one on nothingness, okay, written by this guy, Ray Sorensen. He writes all different things about nothingness, and one of the questions he addresses is, why is there something rather than nothing? And his answer is, well, why not? What I want to claim is that is the correct answer. I mean, he elaborates on it, just as I'm about to elaborate on it, but you could stop there. The implicit message of this answer to this deep question is, not every such question has what you might think of a priori as a satisfying answer. When we ask why is something one way rather than another way, we typically do that in a context of a certain emergent way of talking about the macroscopic world. When you're talking about the universe, there might not be any such context. So there are science questions and philosophy questions. The science questions here include, could the universe have had a beginning? That is to say, we have a Big Bang model, 13.8 billion years ago, there was a Big Bang. Was that really the start of the universe? Or, conversely, could the universe have always existed? Is it possible the Big Bang was not the beginning of the universe, but that there was space and time even before the Big Bang? So the answers are, yes, the universe could have had a beginning, and yes, the universe could have always existed, at least to the best of our current scientific knowledge. We don't know. whether the universe is eternal or whether it had a beginning. It's important to be able to admit where we don't know things. I'm going a lot in these series of lectures claiming about things that we do know. Here's something we don't. We are absolutely ignorant. We just don't understand that part of the universe well enough. We can't reason our way into this answer. We are good Humeans here. We are empiricists. We haven't done any experiments. We haven't made the observations. We can't a priori reason our way into answers to these questions. Then there's a philosophy question. Whichever way it is, whether the universe had a beginning or didn't, is there a reason why it is that way? If it's eternal, is there a reason why there is an eternal universe? If it came into existence at a certain earliest moment, is there a reason why there was that earliest moment? The answer here is maybe. There is a deeper explanation, but maybe not. We don't even know if there is an answer. To the first question, there's an answer. We don't know it, right? Is the universe eternal or did it start? Is there a reason why it's that way? We don't even know whether that's a question that has an answer. So a little bit of elaboration. Could the universe have had a beginning even if anything didn't cause it? Remember Aristotle's argument, one of his arguments, he had a long theory of different kinds of causes for different things. The universe itself ultimately had to have a first cause because it came into existence, he thought. What does science and poetic naturalism have to say about this idea? Well, sure. This is a question we don't know the correct answer to in terms of what actually happened. Could we imagine a sensible scientific theory of the world where the world had an earliest moment of time? And the answer is yes. And I'm using this slightly awkward phraseology for a very important reason. We usually hear people say, did the universe have a beginning? And I'm saying, did the universe have an earliest moment in time? What is the difference between these two things? You know, depends on what you mean by a beginning. Arguably, there's no difference between them. But because we are embedded in time, because we live inside the universe, we have a way of thinking and talking about things happening, where if the universe had a beginning, we think that there was a moment when the universe popped into existence. There was nothingness, and the nothingness was just there, and suddenly, pop, there was the universe. That seems implausible to us. What I'm trying to drive home is that that's not the way it is. That's not the way it would be, even if there is a first moment in time, because time itself starts at the first moment. There is no such thing as before the first moment of time. So the universe didn't pop into existence. That conjures up an image of pre-existing nothingness that converted somehow into somethingness. That is not what is being advocated here. You should only imagine going backwards, not go forward into the nothingness and then the universe exists. Imagine going backward from now. The claim is that if you go backward 13.8 billion years, you reach a point past which you can't go anymore, that there could be an earliest moment. And the question, as poetic naturalists, that we should ask ourselves is, are there plausible scientific theories in which this is what happens, in which there really is a first moment of time? And the answer is yes. There's one, a very famous one by Jim Hartle and Stephen Hawking called the no-boundary proposal for the wave function of the universe. There are long discussions in the physics literature about the emergence of time itself. Time might not be fundamental. Time might just be a good approximation that stops being a good approximation at some point in the very early universe. So it's completely plausible at the level of physics that the universe simply has an earliest moment. It's also possible the universe doesn't have an earliest moment, that it is eternal. Again, the question as scientists we should ask ourselves is not some a priori philosophical justification, but rather, can we build a model? Can we imagine laws of physics under which this could be true? Could we imagine plausible cosmological scenarios in which the Big Bang was not the beginning? And the answer is empirically yes, because people have done it. There's a whole smorgasbord of possible ways that the universe could have existed before the Big Bang. Now, I have to confess, again, another little footnote here, sometimes my cosmology colleagues talk as if they know more about the Big Bang than they really do. They will tell you that the Big Bang was the beginning, that asking what happened before the Big Bang is like asking what is north of the North Pole, etc. They have no right to be talking that way. Sorry, fellow friends of mine, cosmologists. The point is that we have a very good theory of the classical emergent space-time of our universe given to us by Einstein, the general theory of relativity. According to that classical theory, if we go backward in time, there was a singularity at the Big Bang. But that's exactly where general relativity doesn't work anymore. That's exactly the regime in which we have no right to believe Einstein's equation. The Big Bang is not the beginning of the universe necessarily, it's the end of our theoretical comprehension of the universe. So there are many different scenarios where the universe just sails right on through the Big Bang. And I will beg your indulgence to tell you my favorite version of these, which is the one on the bottom right, the baby universes. What we can imagine when we combine our vague ideas about general relativity and curved space-time with quantum mechanics is that empty space itself can have a quantum fluctuation that pinches off a little spherical region of space that then becomes its own universe, a baby universe that then separates off from the bigger cosmos. So imagine that the parent universe of ours is eternal and empty, a universe that didn't have a Big Bang, didn't have a beginning, it just lasts forever. But every so often, there's a quantum fluctuation, it pinches off a new universe. It's easier to make a small baby universe than a big one, so baby universes tend to start small. Most of them will just die and fizzle off, but occasionally the conditions are just right for this universe to inflate, generate a tremendous amount of energy. What would the interior of that universe look like? It would look like a universe that had come out of a Big Bang. That is the kind of universe that could be the universe in which we live. And the best part of this story is that you can play the game in both directions of time. So time is running vertically, but the parent universe has no matter in it. It's empty and quiet. So there's no arrow of time in the parent universe. There's just time, just like space. It has no difference between past and future. But you can evolve it, according to the laws of physics, you can evolve it both forward and backward from the middle. And in both directions, exactly the same thing happens because the fundamental laws of physics work the same forward and backward in time. Namely, you make new universes. You make baby universes. In every baby universe, you start with low entropy, you expand and cool, and entropy increases, and there's an arrow of time for a while before you eventually equilibrate and reach empty space once again. And then they can have baby universes. That can happen to the past just as well as to the future. To the people down there, there are universes where they think that we are in the past. We think that they are in the past. Our arrows of time are pointing in different directions, but that's okay because we can never talk to each other. The whole ensemble is completely symmetric in time, which means that in this example, the arrow of time is dynamically emergent rather than being put in by hand. Is there any relationship between this story and reality? I have no idea. Mostly it's interesting because it is a demonstration by construction that I can imagine a universe where there is no arrow of time built into the fundamental laws of physics. It arises through the natural evolution of a timeless cosmology. So at the end of the day, why are we here? Besides listening to lectures, why is the universe itself here? I don't know. There might not be any answer to this question. There might be, on the other hand. You're allowed to ask it. I'm not saying you can't ask why the universe exists, because after all, there might be deeper reasons we can find. But then what you want to say is, well, why are those deeper reasons true? There might not be any answer to that one. The only rule is that you can't demand ahead of time that there is an answer to this question, why is there something rather than nothing? What is the explanation for my existence? There might be a level at which you say, that's just how it is. Thank you.
And we're still only just over halfway through. There's plenty more to come. It's one of the marks of excellent public engagement, publicly intelligible talks, that not only A, are they publicly intelligible, but that B, they are also illuminating to those of us who understand some of the technicalities. So, which many thanks.
Thanks very much. And I am working on the mind-body problem. So, so one of the things you concede is that human behavior is one of the things that causes a bit of consternation and a bit of debate. And as you rightly say, there's no experimental evidence right now to say one way or the other about whether or not strong emergence might have to be part of the bigger picture. But here's the question. Are you at least open to the possibility of new scientific methods in psychology and new empirical data, which would provide us with a reason to think that, in fact, psychology is in principle irreducible to physics?
Yeah, so almost every question beginning with, are you open to? My answer is yes, in principle. As we talked about in lecture 1, I go by Bayesian theory adjudication, which is to say that to every possibility, there's some credence we have, how likely it is to be true, and we update our credences as we get new information in. And in my mind, it is very, very important that those credences never go to 0. I have a non-zero probability assigned to essentially every idea you could imagine about the universe, because if I didn't, by Bayes' theorem, there was no information that could ever change my mind. And I do believe that if new experimental data comes in, we must be always, as good scientists, willing to change our minds. So my point about consciousness was, and strong emergence, is that it's not, I didn't quite say we have no evidence for or against it. I said we have no evidence for it. I think that the evidence in a Bayesian sense we have against strong emergence is the enormous empirical success of the core theory. We have a theory in which strong emergence wouldn't happen because of causal closure, and I think that it's a presumption. It's basically, the lesson I'm trying to get across is, if you want something like strong emergence to happen, here is what you have to get rid of. Here is the success you have to throw away. And in my mind, it is very unlikely to become necessary.
Question over there at the end.
I was just going to ask if our universe was a baby universe from like an eternal state universe, and it continually expands, and there's a crunch eventually, will that create another singularity back into the eternal universe?
Well, yeah, that's a good question. In some sense, so the question is, could one of these baby universes expand for a while but then recontract? They certainly could. Would they then sort of rejoin the parent universe? We wouldn't expect that. The idea, if you sort of go through the math a little bit here, is that the reason why these baby universes can continually be generated is because doing so increases the entropy of the whole shebang. So it's not, when a baby universe dies, it's sort of, its entropy is still there in some sense in the accounting for everything. It would not be reabsorbed by the universe. That would be like a reversal of the arrow of time. All this very speculative, so you can't take my word too strongly for what would actually happen.
And the next question was up at the back.
I guess my question follows on from that one. It was that you said that the baby universes come out of quiet, empty parent universes, which reminded me of how you described the way that ours will finish up. So can a baby universe come from a baby universe, if ours was one? And do they get, sort of given their pocket money, they've got as much energy and mass as they'll ever have? Or is that something that grows as they are born?
Good. So short answer to the first question, yes, baby universes can grow and mature and have their own children infinitely long into the future. This is, the whole point here is that we're explaining why entropy is observed to be increasing in our universe by claiming that in the universe as a whole, entropy can always expand. It is a finite number. It's not infinitely big, but it has no upper limit. You can always increase it by making more and more universes. So universes have their babies, and they have their babies, and so on ad infinitum. You might have issues about, well, you know, where does all this stuff come from? Where does all the mass and energy and so forth? And I guess, yeah, I should have said that. I meant to say that out loud. But this goes back to the idea of creating a universe, or having a universe that has a first moment of time. So I didn't read this out loud. Our universe seems to be the kind that could have had an earliest moment of time. Why? because it seems, as far as we can tell, that the total energy, the total mass, the total electric charge of our universe is 0. Of course, we have stuff in our universe, so you might say, well, this has energy that's not 0. What are the chances that the energy of the entire rest of the universe is exactly minus this? Well, the chances are very good. It turns out to be a feature of general relativity that if you have a closed universe, no matter what is going on inside, the gravitational energy inside exactly cancels the energy of the stuff. There's positive energy in matter and radiation, negative energy in the curvature of space-time. It all adds up to exactly 0. So it costs nothing to make new universes. That's why this kind of mechanism is so fun and tempting to put to use, because it can happen without limit.
Question right there.
Just with this, because if the parent universe doesn't have time, then how could the quantum fluctuations create a new universe? Because that would itself require time. So is there anything there?
The parent universe does have time. It does not have an arrow of time. Those things are very different. Just like in outer space, there is space, even though there's no arrow of space. You know, you and I, in our experience of time, in our idea that time is flowing and so forth, all that is because time has an arrow. But if the arrow goes away, time doesn't go away. It's still a label on different moments in the history of the universe.
And in the corner there.
I want to return to the subject of the first question, namely behavior and consciousness. I'm entirely happy to accept that, in principle, physical systems could lead to an entirely satisfactory account of human and animal behavior. But we could be zombies. The fact is, we are not zombies. We have consciousness, awareness, etc. Are these not different in kind from the things that physical mechanisms can explain?
Good. So zombies, you said? Yeah, Scottish accent, sorry. I don't think we could be zombies, is the short answer. The even shorter answer is come back Wednesday when I will talk about consciousness. I won't talk about it very long, and I'm happy to give you the short version. I don't think that zombies are even conceivable. It's very much like saying, you know, could you imagine, zombies, I need to tell you what this is. The idea of a zombie is a thought experiment from David Chalmers, a highly respected, a great philosopher, who says, look, consciousness is clearly not reducible to physical stuff, because I can imagine a being that is physically exactly the same as me, and yet doesn't have consciousness, does not have inward awareness, qualia, experiential, subjective, first-person experiences. I think that he's fooling himself. I think that he can't imagine it because it relies on a certain, I think it's begging the question. Can you imagine a universe in which water is not H2O? Well, you can't, because water is H2O. But before you knew that water was H2O, if someone said, could you imagine a universe in which water is not made of hydrogen and oxygen, they might have said, yes, I can imagine that, because they don't know. By learning new things about things, what we thought was conceivable changes. I think that once we understand what consciousness is, namely an emergent phenomena from the underlying physical stuff, we will realize that when you have exactly that physical behavior, consciousness is coming with it.
Here at the front and then at the end.
You said a couple of times that the reason that we have an arrow of time is because we start at a low entropy state and then we have to move into a higher entropy state, and then that is the arrow of time. We're pointing towards higher entropy. But if you don't assume that time exists to begin with, how can you say that entropy is increasing? How can you be talking about a change over time if you don't have a direction of time to begin with? Because the way I understood the reason that entropy increases is because if you have things moving about randomly and you've got more ways that one particular outcome can happen than another particular outcome can happen, that it's more likely that that's going to happen, so entropy increases in that way. But if you don't have things moving about in time to begin with, why should entropy increase? Or how can you even think that entropy increasing is a sensible way of talking about things?
Right, so it's related to the question was asked earlier. There is time in this universe. At every moment, see that it's in magenta over on the left. There's definitely time. There's definitely the flow of time. You tell me, you be Laplace's demon, you tell me exactly the state of the universe on any moment in time. I can evolve it in time, both forward and backward. If you live in the parent universe, there's no arrow of time. You don't see anything happening any differently, forward or backwards, because nothing happens at all. But secretly beneath what you can see, the quantum state of the universe is still evolving with time. And that's because you have the option of creating more universes. So the game that we're trying to play in this scenario is to say, in the connected parent universe, the entropy is as high as it can get. It's empty space. But in the bigger ensemble, entropy can still go up by making new universes. And entropy can always go up. So let's say you think, well, you cheated because you only gave me one connected universe to start with. So I say, fine, tell me what to start with. No matter where we start, entropy can always increase. The game we're playing is, you give me an integer, I can always give you a bigger one. Now, that might be cheating. That might be playing games with infinity that is not quite physically realizable, but I think that we have no reason to discard it as yet.
No, it was at the end there. Then I think...
I was actually going to ask a pretty similar question, to say that if we're going from a low entropy state to a high entropy state now, what would the parent universe be like entropy-wise? But sort of answered.
Good.
I'm not sure if what I'm thinking is right or wrong, but this lecture has a lot of metaphysical stuff than physical stuff. Well, my question is, you're making so emphasis on the laws of nature, and you said in the last lecture that laws of physics applies only for the 5% of the universe that we know about, and the 95% of dark matter and dark energy, we know nothing about these laws. And on the other side, the baby universe hypothesis, there is no, to my knowledge, there's no scientific way to prove the existence of, to prove this theory or not. So 95% we don't know nothing about the laws of nature or laws of physics of this 95%, and this hypothesis, we have no way to prove it or not. So why not to give us a room for another God hypothesis, which may give more plausible answers for the why questions, and put it aside with these hypotheses, as long as you're open to any hypothesis, even though we cannot prove. Thank you.
Sure. So, okay, there's a lot going on there. So number one, it is not accurate to say we know nothing about dark matter and dark energy. We know, actually no, we know a lot about dark matter and dark energy, how they behave, where they are, how they're distributed through the universe, how they evolve through time as the universe goes. We don't know the specific identity of what they're made out of, but there's every indication that they obey very, very typical vanilla laws of physics, which is exactly what you would expect. That's what we observe. Number two, anytime you use the word proof in talking about scientific hypotheses, you're already on the wrong track. Science does not prove things. Science increases or decreases our credence in different things. So no, we cannot prove that there are universes in the past like that. I cannot prove the existence of Edinburgh, you know? I can give you evidence that it exists. I was there yesterday. But I cannot prove it, because you could say, well, I don't believe this, picture you're showing, maybe you just painted it, etc. Proof is not the point. The point is, what is the probability we should assign that this theory is probably right? Right now, I think the probability we should assign that this theory is right is pretty low. And I say that as it's my theory, right? We don't have a lot of good evidence for it. We don't understand any of this stuff. It's beyond our current state of knowledge. But I can imagine increasing our state of knowledge by observing things here in the observable universe to the point where we had a sufficiently good grasp on the laws of physics that we said something like this is probably true. Finally, why shouldn't we admit the existence of God or something like that? Well, again, as before, we should admit that as one of the hypotheses that is absolutely included in our Bayesian credences. What I'm saying, without talking about God very explicitly here, is that there's no need for God in the traditional sense. We can certainly imagine completely self-contained descriptions of the universe that work perfectly well. And then we can decide for ourselves whether or not which of the different hypotheses fits better the universe we actually observe.
These are terrific questions because they're budding off, terrific answers because they're budding off questions like nobody's business.
Good,
Now,
yes.
I don't think we're going to get through all the whole queue,
questions.
but I think
Baby
that the queue currently is about 6 people. So I think you had a question there, and there was one at the back, and then we might not get as far as you.
You seem to be saying that there are all these real descriptions of nature, but using the word fundamental for one of them. And so why not flip it around and say time is fundamental, and if you grind this down, the other things are like a de-emergent kind of description of the universe. Why do you give primacy to things which are small, I think is essentially the question.
Good. I think that's an interesting question. You know, and I alluded to this right at the beginning, but I didn't go into details about it. In practice, as we describe the universe we actually see, what we call the lower levels match on to what we also call microscopic. If we're being more careful, what we really mean is not more microscopic, but more comprehensive theories of the universe. The real question is, which sets of circumstances are accurately described by the particular theory under consideration? The theories that we informally think of as microscopic are really those that could, in principle, describe a wider variety of circumstances. The air in this room could, in principle, be described by the core theory, etc. And as you go up, there's a smaller and smaller regime of applicability. But in practice, it's really, you know, ignoring things that are going on a small scale, so we informally use that. But I'm actually in favor of being a little more careful there. So sometimes when I'm in the careful mood, I will say more comprehensive or more coarse-grained, less comprehensive theories.
I think we may have time for just one more.
You're the boss.
In which case?
Is this on? Yeah, sorry.
Welcome.
Yes, I might be making wrong presumptions here, reading into some of the things you've said, but it seems that you have a fairly necessary view of the laws of physics, of the laws that govern the universe. That we don't necessarily know everything about them, but when we do know about them, at least they necessarily exist. But also, when you were talking about the emergent levels, what you define as real is a fairly pragmatic thing. What is it useful for us? What's the useful level of description? Or what's the most, so free will is a useful level of description, even if we really don't have a choice to act in a different way. So I'm wondering how you reconcile that pragmatism that seems to be at play in your description of emergence, but also a necessary view of the laws of physics.
Yeah, I'm not sure where the impression came from. I would not apply the word necessary to anything going on here. Comprehensive versus coarse-grained, I would say. In some sense, I want to be a pragmatist all the way down. There's an instrumental motivation we have, namely describing what happens in the world. I find the fundamentalist, the most comprehensive theory we have right now, the core theory, I mean, it's very, very far away from necessary in the sense that I could easily imagine the world having completely different laws of physics. I take it to be an empirical fact that I have high credence in because of everything that I've seen about the world, that there are laws of physics that seem to always work, that seem to govern everything that we know. We need not have found ourselves in a universe like that. I don't know if you were here earlier for the other lectures, but I went against metaphysical certitude and a priori reasoning of all sorts. I think that we should just be completely pluralistic about hypotheses and completely empiricist about how to judge them, with some small caveats. But basically, I'm very open to other possible worlds. And the world we actually live in, given our current state of knowledge, is an ugly mess, right? There's so much we don't know about it. It looks very far away from something that is pristine, clean, and necessary. We're hoping that the more we learn, the more elegance and simplicity gets revealed by future investigation. But I actually argue against my physicist colleagues who have this aspiration of someday finding out that the ultimate laws of physics are in some sense necessary. I think there will never be a sense in which they were necessary.
And there, I think we could go on almost indefinitely, but stamina forbids. So I'm sorry to those who had questions which couldn't be asked. And so the last main task this evening is to thank Professor Carroll again and welcome you to the next on Wednesday. Thank you very much.